Let's look at some kinematic models in more detail. The first one we'll look at is called differential or tank drive. And in this configuration, we have two wheels that are set in parallel and independently driven. The idea here is that if both of the wheels are rotating in the same direction, then the car will move forward as both of them drive in the same direction. However, if both of the wheels are driven in opposite directions, then that causes a net force of zero. The car doesn't move anywhere, but it does rotate in place. These are the most basic configurations of this particular model, but we can apply some trigonometry and get a more complicated model that allow us to do things like drive in a curve. So here's our simple model. We have our two wheels that are driven independently. The R represents the wheel radius and L represents the wheelbase length, the space between the two wheels. And then we also have some extra variables here called the left and right wheel angular velocity. So it's how fast they're spinning. You can think of it as RPM. And we have the current heading, which is the theta for the robot. Now we have some intermediate variables here that are going to make our math a little bit simpler. The first is the average angular velocity of the wheels. So this is the left and right wheel angular velocity added together and divided by 2. And what this does is gives us how much on average the robot is going in the same direction, how much on average the wheels are going in the same direction. If they're exactly opposite, then this is 0 and the robot should turn in place. If they're exactly the same, then this is the same value and the robot should just roll forward. We also have the differential velocity of the differential angular velocity of each of the wheels, and this will allow us to tell how much the robot should be turning as it's moving. So putting these together, we get the change in x and y positions as the radius times the angular velocity. These are in radians, that's why this works, times the cosine of the current heading of the robot. And that gives us the delta x. Delta y is the same with sine of theta. And then the change in theta, the change in heading, is the radius of the wheels divided by the wheelbase times the differential angular velocity. So this tells us how much it's going to turn during this one tiny time step, right? So this only works if we have very, very short durations between the times that we're updating this. So a very, very small delta t gives us our change in x, change in y, and change in theta. So if we want to get an accurate representation of where the robot's going to end up, we have to do this a whole lot. Actually, the more often we do it in our simulation time, the more accurate we'll have our resulting position be. And you can kind of see here from the relationships that we can get something that turns a curve at the same time, right? So if these are non-equal and and not in the same direction, then we'll get something where it's turning and the overall velocity, overall forward velocity is not the same, so we'll end up carving out sort of a curve as the robot moves, which is pretty cool. We can drive in a circle like we do with our steering car, but we can do it with the differential wheels. We can curve out an arc rather than doing go forward, turn in place, go forward, turn in place sort of thing. We can drive in an arc. The simple car, the Ackermann car, works very similarly. We have except in this case, the wheelbase is between the front and rear axles, and we have an additional theta, which is our steering angle, right? So we have, we're going to represent the overall car speed as s, and we could, that's where we got the radius of the wheels times the angular velocity of the wheels. That's going to be the same for all of the wheels on our Ackermann car. The overall speed should be the same for everything. So we're just going to represent that using S, and our L again is the axle to axle length. The steering angle is how far the front wheels, the steering wheels, are tilted off of the primary axis of the car, and the current heading again is theta. Now in this case, the idea here is that as the steering angle increases, basically a radius of a the radius of a circle is traced out. So our delta x and delta y is very similar to the differential car, because basically the wheels are going to follow, the rear wheels are going to follow whatever direction it's currently pointing, but the front wheels are going to cause it to rotate basically as the tangent to a circle. And that's exactly what we see for the delta theta, that it ends up changing the angle of the car as it drives around a particular as it drives around a circle that's sort of swept out by the steering angle. A more complicated version of these drive systems is called Omnidirectional Drive, and there's two different kinds of those. The first one is called Holonomic Drive, where we have these special omni wheels that allow it to slide in a direction, and they kind of look like this. And it's basically a drive wheel that's made up of a whole bunch of little rollers. And the idea here is that we can apply force when the wheel is rotating in the direction as the same plane as normal, but it can slide sideways, so there's no sideways friction. And what that allows us to do is when these rotate, they exert a force this way, and this one exerts a force this way, and because they can slide, this one can move sideways, and by coordinating the speeds of the wheels, they can move in different directions. A variation on this is called Mecanum Drive, and these wheels have tilted rollers instead of 90-degree rollers. So when these roll forward, they exert a force of 45 degrees rather than a force directly ahead. Let's look at an example with this. So with the Mecanum Drive, each of the wheels, if they're all rotating forward, they all exert a force that's 45 degrees from their primary axis. Depending on which way the rollers are oriented, if they're right-handed or if they're left-handed, these will exert different forces. So in this case, we've got a right-handed wheel opposite a left-handed wheel, and what happens is the components of those forces end up canceling out. So each one of these, because it's exerting a force of 45 degrees, some of it is going forward and some of it is going sideways. The parts that are going sideways cancel each other out, and we end up with an overall forward motion that pushes the vehicle forward. Now what's cool is if we coordinate these wheels, if we put some of them backwards and some of them forwards, now the forces are reversed. So we end up with a 45 degrees still, but in the opposite direction for the wheels that we reversed. If we look at the components of these, the components that are going forward now cancel out, right? So I've got an equal force going forward, an equal force going backwards, and the same on both of the rear wheels, and what's left is these components that are going to the right, and we end up with an overall right traversal trajectory. Now, by coordinating these behaviors, we can get any motion from any coordination. So we can slide directly sideways, we can rotate in place, we can rotate while we're moving, we can do all kinds of stuff. And these are actually used in industry in things like forklifts that need to navigate tight spaces and aren't able to do things like turn around or rotate or things like that in the tight aisles of factories and warehouses.